We now look at the binomial series. Find the Maclaurin series for the function f of x equals the quantity 1 plus x raised to the k power, where k is a real number. As usual, we start taking the derivatives successively. The first derivative is k times 1 plus x to the k minus 1. The second derivative is k times k minus 1 times 1 plus x to the k minus 2. Using the power rule, the third derivative is k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. We see that there is a pattern here. The nth derivative, we end up with the power k minus n. And so the n derivative is k times k minus 1 times k minus 2 all the way to k minus n plus 1 times 1 plus x to the k minus n. We then evaluate these derivatives at x equal to 0 because we're looking for a Maclaurin series. F of 0 is 1. F prime of 0 is k. F double prime of 0 is k times k minus 1. Because 1 plus 0 is 1. 1 raised to the k power is 1. The n derivative evaluated at 0 is k times k minus 1 times k minus 2 times ... all the way to k minus n plus 1. So the n derivative evaluated at 0 is the product from k to k minus n plus 1. Recall that the Taylor series is of the form c sub n x minus a to the n, where the coefficient c sub n is the nth derivative evaluated at a divided by n factorial, but in this case, a is 0. And so the function f of x equals 1 over x to the k is the sum, the n derivative evaluated at 0 over n factorial times x to the n. But the coefficients are k times k minus 1 times all the way to k minus n plus 1 over n factorial, and then x to the n. But this coefficient is K2's n, which is a binomial coefficient. That the function 1 plus x to the k is the sum of K2's n as the coefficient times x to the n. This is 1 plus kx plus k times k minus 1 over 2 factorial x squared plus ... The n term is K2's n x to the n plus ... This is known as the binomial series because it involves the binomial coefficients. Note that K20 is 1, K21 is k, K22 is k times k minus 1 over 2 factorial, and K2's n is k times k minus 1 times all the way to k minus n plus 1 over n factorial. By the ratio test, if we look at the limit of the ratio of a sub n plus 1 over a sub n, note that the a sub n plus 1 is the a sub n term being replaced with n plus 1. So the binomial coefficient is the product from k all the way to k minus n divided by n plus 1 factorial. We can simplify the coefficient k minus 1 all the way to k minus n plus 1. We end up with k minus n times x over n plus 1. Because x to the n plus 1 is x to the n times x, cancelled out x to the n, and n plus 1 factorial is n plus 1 times n factorial. We factor the absolute value of x to the front of the limit. We end up with the limit of the absolute value of k minus n over n plus 1, which is 1. And so the limit is the absolute value of x, and by the ratio test, this series converges if the limit absolute value of x is less than 1, or negative 1 is less than x less than 1. For example, find a series for the square root of 1 plus x. Let f of x equals the square root of 1 plus x, which is the quantity 1 plus x to the power 1/2. We recognize that this is the binomial series with k equals 1/2. Note that the binomial series 1 plus x to the k is the sum of k choose n times x to the n. When n is 0, the first coefficient is 1 half choose 0. When n equals 1, the second coefficient is 1 half choose 1, and then 1 half choose 2, and then 1 half choose 3, and so on, with the factor x to the 0, x to the 1, x squared, x cubed, and so on. These coefficients can be evaluated using the formula k choose n, which is the product of k times k minus 1 all the way to k minus n plus 1 divided by n factorial. So 1 half choose 2 is 1 half times 1 half minus 1 over 2 factorial, which is minus 1 over 4 over 2, negative 1 over 8. And 1 half choose 3 is 1 half times 1 half minus 1 times 1 half minus 2 over 3 factorial. Observe that we choose 3, so we end up with 3 factors in the numerator. The last factor in the numerator is k minus 1 less than n. Simplifying this, we have 1 half times negative 1 half times negative 3 half divided by 6, which is 3 over 48 or 1 over 16. And so the square root of 1 plus x is 1 plus 1 half x minus 1 over 8x squared plus 1 over 16 x cubed minus 5 over 128 x to the 4th plus dot dot dot. We can use this series to come up with many more series. For example, if we replace x with negative x squared, then we end up with a new series. Simplifying this, we will end up with the square root of 1 minus x squared equals 1 minus 1 half x squared minus 1 over 8 x to the 4th minus 1 over 16 x to the 6th plus dot dot dot. We use this function, the square root of 1 over x, to obtain another series representation for another function. For example, if we replace x with negative 1 over x, then we end up with the square root of 1 minus 1 over x equals 1 minus 1 over 2x minus 1 over 8x squared plus 1 over 16x cubed, and so on. Note that we can use the first few terms to approximate the function. We can use the first few terms to approximate the radical function, as long as the absolute value of x is small, or with the last series, as long as the absolute value of 1 over x is small.